Okay, so thank you very much. So let's start with the plenary talk of this session. So it's going to be given by Xiangyu Cao from École Normale in Paris, and please, Scrambling and Instability in Large and Quantum Systems.
Okay, thank you very much, Leticia. So I would like to first thank the organizers for putting together this wonderful conference, and I'm really honored of the opportunity to speak here. So I guess you can hear me correctly. Okay. So I'm going to talk about scrambling and instability in large and quantum systems. So of course you would ask what scrambling means. Okay, to be honest, I'm also figuring out myself. So we shall see together. In particular, my general goal is to bring this concept which has been made popular mainly by the quantum information and the high energy in particular holography community a bit more down to earth, so and understand it in more simple terms. For example, in terms of instabilities that can happen in these systems. Now the other keyword in this title is large and quantum system. So I would like to start by explaining what that is first. Okay, so we know that many-body physics is hard, and many-body quantum physics is maybe even harder because it's essentially you hit a wall of exponential complexity when you try to do any numerical simulation and so on, and it prevents much progress from being made, and there are two exceptions. So there are two kinds of limits where we expect that you can do controlled calculations. One such limit is the semi-classical limit. So where h bar is much smaller than the typical action scale that you are considering in the system. Usually you set h bar to be very small, and you take everything else to be order 1, then you can retrieve the well understood classical limits. For example, if you solve a Schrödinger equation on a state and B-yard, and if you go to very high energy, then you will be in a semi-classical regime, and you will retrieve this the classical B-yard whose egotic dynamical properties are better understood, and in that limit, your operator's commutator will become just the Poisson bracket, and they will become essentially commuting numbers, and then you can write this kind of equation of motions, which you can put on the computer. So this is the well understood semi-classical limits. Now, recently there has been much interest in another limit, which is called the large n limit. Of course, it is not invented in the last decade. It went back to 't Hooft, and so in the last century. But in the last decade, this kind of model has become very popular. It's a OTOO interacting model. You can hear these numbers can be are usually fermions in the now well-known Sachdev-Kitaev model. But however, for statistical physicists, this is also very well known as a p-spin model. If you consider that these are bosonic degrees of freedom. So now, if you go in and read papers about them, you will see that you can do controlled calculation in the large n limit on these models, but the calculations you do are very different. So you cannot write this really. You cannot really write this kind of equation of motions. What you can do, for example, is to write diagrams that you can resum to calculate your correlation functions. You could try to express these diagrams in terms of equation of motions, but if you do that, you will find out that these equation of motions are non-local in time, and usually integral differential equations, which are quite horrendous. For the experts, you can do that in Kaddish field theory, and I won't write down the equations in that formula, and it's quite heavy. Okay, so there are these two. So So apparently they are not very comparable. So one of the goals of this talk is to compare them in some way. Sorry. So now let me introduce the concept of scrambling from a semi-classical point of view first. So in that context, we can motivate that by as an attempt to quantize the butterfly effect. So if you take your favorite chaotic system like a state and BR, then you know that a typical trajectory is chaotic. So if you perturb the initial condition a little bit, then two neighboring trajectories will deviate from each other exponentially fast like that. So how can you quantify that? You can do this trick. So you want to know the sensitivity of some of your position at of the deviation at time t with respect to a perturbation at time 0. So this you can turn into a Poisson bracket, and then you can make it a quantum by turning the Poisson bracket into a commutator. Now this is an operator. So what you can do is to square this and then average over some ensemble. So why should you square it? Because if you don't square it, then this then even this classical number, it can be positive and negative in the whole space, and if you just average that, you won't get the positive and negative part will cancel, and you won't get exponential growing stuff. You have to average it because it's an operator. If you want a number, you have to average it over some thermal ensemble. So usually it's some thermal ensemble. Now, as Jorge told us yesterday, it's a good idea to split this thermal ensemble into two halves and sandwich them and sandwich the commutators between. But you could also not do this. Now. From what we know from classical chaos, you expect that this object would grow exponentially with an exponent which is known as the Lyapunov exponents which characterize a classical butterfly effect. So the physics of this object has been much studied. In fact, this object was also not new. It first appeared in a paper on superconductivity by Lakin and of Chinnikov in the 60s, if I remember correctly. But it regained interest recently due to a serious paper from a high energy community and also quantum information community, especially by Kitaev and Amanda Chen, Stanford Shanker. So I should point out that in general, the physics of this object is very different if you look at it at infinite temperature or at very low temperature. Now the infinite temperature limit is simpler, and in fact I will first speak about the infinite temperature, and that limit allows us to gain some basic intuition about this object, and to also to clarify some basic confusions which was around about this object, and also allows us to compare larger and semi-classical in a way. Now then I will come to this limit, which is much less trivial, and also on SYK large N models. Okay, so to do that, let's take a very simple example of an OTOO spin model. So you consider a number of spin halves from 1 to n, and you consider the so-called Lipkin-Meshkov-Glick model, which is some magnetic field in x direction, and then some OTOO interaction in z direction. So okay, so this is an OTOO model. You can think about it actually in two ways. You can think about it in the sense of a usual classical limit, where you say, okay, this sum of xi, and here it's really sum of zi then squared. These operators are just also spin representations of SU2. So you can think of them as just a spin S operator, where S is related to N in a usual way. So you can consider a classical Hilbert space of this dimension of just one spin S. And now the correct classical variables to look at it are these ones, because we are looking at the Hilbert space where all the spins are aligned. So if you want to normalize them correctly, you have to divide it by S. So that this object has a unit length. Once you do that, then you obtain a classical limit where whatever quantum calculation you want to do is, for example, the equation of motion becomes some Poisson bracket where f is some function of x, z, x, y, and z. And also, if you want to take a trace, classical trace, it becomes an integral over the classical phase space, which is a unit two sphere. Now these will become quite different in a quantum case. You can already see that everything is different, but I will come to that. After. You will see the slide again, so don't worry if you haven't read everything. Okay, so now let's consider scrambling in the semiclassical in the semiclassical sense. I still consider this model, and the point I want to make is that although scrambling or out of time autocorrelator is motivated by chaos, it is not equal. It is not the same thing as chaos. It can also come from instability, and here is a very simple example illustrating this. So if you take this classical Hamiltonian, if this interaction is strong enough, then on the two-dimensional phase space, which is two-sphere, you can find a saddle point and instability, or if you draw it in two dimensions, it looks like this. So the trajectories will go in like this, and then go out like this. Okay. Then I can compute the classical out of time autocorrelator. So I write this object, and then I make everything. I take the classical limits, so it becomes an integral over this sphere, which I draw like a map of the world, of some dependence on some sensitivity on initial condition. So now what's going on is that you can bound from below this integral by considering a very tiny region around this instability. So this width here has to be very small. If this width is very small compared to the time where omega is the local instability exponent, so how exponentially fast this ball will fall down. If you start from very close to this point, and you will stay very long time to this near this point, and then you can linearize the dynamics. So then if you plug this in, you will see that you get 2 powers of exponential omega t, and the volume is 1 power of exponential minus omega t. So you still get an exponential of omega t. So just from one single instability, you get the so-called scrambling. So this model is, of course, it has two-dimensional phase space. It is integrable. So there's no dynamical chaos whatsoever. A single instability saddle point does not qualify as classical chaos, as is well known. So actually now you can. So this is sounds unbelievable, but you can actually do the quantum calculation. So not at s equal to infinity, but at some large spin, and you can really see the exponential growth. And it is just contributed by the energy level of that saddle point. So the scrambling is really generated just there. So okay, so this is about semi-classical scrambling, which can come from instability. It's not chaos. So now what about the other point of view? So you can say, okay, but you were cheating. This is not really the Hilbert space. If I have n spin 1/2, this is the Hilbert space. The Hilbert space is exponentially large. It's dimension 2 to the n. And in this Hilbert space, if you take if you want to view it classically, you should think of these spins as being very disordered. They are not aligned. So if you take this object, the sum of spins, then you should somehow apply central limit theorem. And you want to define a collective variable, you have to divide by square root of n instead of 1 over n here. And now, but once you do that, and normalize your Hamiltonian appropriately, you can write exactly the same equation of motion for observables. But the traits over this quantum Hilbert space, so the full Hilbert space is not different. It's not on the 2 sphere. It's actually on the 3-dimensional space, and there's a Gaussian measure. So it's really essentially limit theorem at work here. Okay, so then what about scrambling if I do the real quantum calculation? So if you look at how scrambling is defined in the quantum many-body context, it is actually slightly different from what I did earlier. So the classical OTOC is a square of the commutator, and with respect to this sum object. So it's a sum of J and Sj. Okay, and then you have to sum the whole thing. So if you write everything out as a double sum, whereas whereas the quantum in quantum many-body models usually is defined in this way. You consider the commutator with just one single spin 1/2 operator, and then you square it. And then if you want, you can sum over i's afterwards, but it is usually not needed because if it's OTOO, every I plays the same role. So this just gives you some n factor. So you can actually not have it. Usually people don't put it. So this one has a clear classical interpretation. But what about this one? Because I'm not working on spin S operators anymore. These are not symmetric under the permutations of my spins. But this object has a different interpretation, which is somehow nicer from a quantum information point of view. It's an interpretation as an operator size. So for example, if you imagine that this O of t here is just a x1 times x2 times this, so it's a Pauli string of little n operators. Then you can convince yourself that this quantum OTOC is here is just the n. It's counting how many factors there are, because this commutator actually can hit one of the terms. In general, if you have a linear combination of these kind of Pauli strings, then you should then this will be a quantum average over amplitude squared. So why is this a nice interpretation in terms of quantum information? Because if you think about how an operator evolves, say I start from a single spin operator, then I hit the Hamiltonian, I can become under Heisenberg time evolution, I become 2 spins. Then the 2 spins will become it will hit the Hamiltonian again, and so on and so forth. So you can imagine the operator growth in the space of operators as this kind of a tree process. So this is also how information spreads. You start with some information about one spin, but and then under time evolution, the information is spread into something which is very inaccessible about many spins, but it is conserved because everything is unitary. So this is what people call scrambling. It's the information is conserved, but in an unrecognizable way. Okay, so this interpretation is nice, but this looks very formidable to calculate, right? I'm losing my intuition from classical physics. However, recently we found by a little trick that actually you can still write a phase-space representation of this object, even if you intuitively it is not that obvious. In fact, it's very similar. You still have something. It still reduces itself to an integral over the phase space, but now it is a three-dimensional phase space of some gradients of your operator then squared. So now a very curious thing happens. Because I'm not integrating over just a one two-sphere, but a layer of two, but many two-spheres indexed by the radius r. I'm integrating over the three-dimensional space. And this picture is still true for any r constants, but when r is very large, you can convince yourself that because of nonlinearity, the dynamics becomes faster and faster because your spin is growing longer and longer, and the instability exponent of this fixed point will be also growing with r in some specific way that you can compute, and so you can repeat the previous calculation. But now you get a saddle point dominated contribution, which is like this, which is dependent on r, and then you have to integrate over OR, and you do and by some saddle point calculation, you find the growth of this correlator, which is super exponential. So if you think about this tree on the previous slide, it is somehow counterintuitive, because if you write any kind of epidemic-like model of the growth of the tree, you will expect exponential growth in an OTOO model. But instead, in fact, you can find a super exponential growth. So the intuition, the partial intuition of why this happens comes from actually the peculiarity of this kind of model, which is a super extensive spectrum. So you remember that in a previous slide, there's some detail about how you normalize the Hamiltonian. So what happens is that if you normalize your Hamiltonian in this quantum way, then you will find that the ground state energy of that Hamiltonian is super extensive. It's not proportional to n, but n to some power larger than 1. So it means that when you start to probe the system for longer and longer time, you start to see that there's something wrong at away from the center of the spectrum. And that is essentially why you can get this very weird thing. Also, it does not break any known bound on scrambling, including ourselves, for exactly the same reason, actually. Okay, so now that we have some intuition about okay. So just before moving on, I want to make an experimental remark, because this OTOO model seems quite strange or peculiar. Actually, it is actually quite natural. For example, in atom cavity, in cold atom experiments where they put atoms in optical cavity, what they do is that they generate interaction between atoms by coupling them to a cavity, and then so it's essentially some atomic spin degrees of freedom coupled to a cavity. And now if you integrate out the photonic modes of the cavity, you will get some OTOO interaction between the spins, provided that this cavity mode is delocalized in the cavity. And for example, for example, they can engineer this kind of Hamiltonian, which looks much like the one I was discussing. So it's not pure fantasy. This kind of Hamiltonian. Okay, so far I discussed exclusively scrambling at infinite temperature, which is on which you can develop some kind of intuition. But now this is a real question for especially for holographers. What about the SYK like large N systems and the low temperature? So okay, you can ask, we saw that scrambling can come from instability. So are there instabilities in SLK-like systems? The answer is yes, I will show you. And it's actually quite interesting to look at them. And then can we understand the so-called fast scrambling or maximal chaos of SYK models at low temperature as relating to these instabilities? And the answer of that is not yet, but I will provide some speculations if time permits. So what is this fast scrambling and maximal chaos? It's simply the statements which was proven by Kitaev that if you consider this object at low temperature for SYK-like models, he showed that the Lyapunov exponent is proportional to temperature, so beta is inverse temperature, with a particular prefactor, and these people proved earlier that the chaos cannot be stronger, so this number cannot be larger than that, okay, I think in the next talk by Silvia Papalardi, she will explain more on this and how you can also understand this, but I'm not so here I'm not going to understand to explain this in more. I want to come back to instabilities in SYK-like models. So okay, so in the first slide I wrote on SYK like a p-spin, like a fermionic p-spin model. However, there's actually a simpler way of understanding, at least starting to understand SYK-like model. With the spin models that we wrote down. So this is the spin model that I wrote down, and we kind of understood it. Now the recipe of going from a spin model to SYK-like model is that you should replace each collective spin variable by a fermion bilinear operator. So it's a quadratic operator in fermions, and as Kitaev suggested, they better be random. So essentially, I replace this by HS and this guy by Q squared, and both HS and Q are some OTOO fermion bilinears with coefficients drawn from some kind of random matrix. So I didn't write, but they are centered Gaussians, independent Gaussians with suitably normalized. Which should reflect how you normalize this guy. Okay, so this is our baby SYK model now. So in fact, it was I didn't invent it. It was essentially in an early paper by a Santa Barbara group, Senke Xu. So in fact, in this model, you can find a phase diagram which looks much like the spin model. So remember this kind of energy landscape of broken symmetry. You can also find it in this model. So basically, I'm drawing here is a phase diagram on the coupling constant and the temperature, and in this half of the phase diagram, and the effective potential for the boson, which you can obtain by some standard large N technique, it looks like this. So there's a quite standard transition here. Symmetry breaking phase transition here. And now a good thing about this is that, oh, I didn't talk about what the boson is. So let's see. I think in the next slide I will tell you what the boson is. Sorry. Yeah, in fact, the slide with the boson is here. So what is the boson? The boson is obtained if you Hilbert-Synovich decouple this quadratic operator, and then you can view it as Q coupled to some bosonic degrees of freedom, and then you get also a free Hamiltonian for this boson, but in some massless limits. So in this sense, we can also view this as a kind of SYK boson model, which in analogy with the spin boson model, which is a paradigm of old school paradigm of open quantum system, where you couple a system to a path, to a bosonic path. So now we can understand this. So in this phase, in either the boson does nothing or it condenses. So in any case, you can treat it classically. So this is pretty nice because we are regaining classical intuition. So in fact, you can even do dynamics of this. You can write down the equation of motion for the boson near the saddle point if you have an instability, and it is kind of different from what you expect because it is nonlinear, it's non-local in time. So it's a convolution with some retarded Green function, which we can compute, and then you can look for instability solutions, so exponentially growing solutions, and determine the exponents. In fact, you can show if you are near the critical point where this inverse parabola is very flat. That lambda is actually linear in the distance to the critical point, which will give you a correlation time of inverse the distance to the critical point, which we will see can be useful. And now, can this saddle point contribute to scrambling? Well, let's see from a simple energetic argument. So you can easily estimate the energy of the saddle point with respect to the true ground state energy. It is also proportional to that. So if you want that to contribute to scrambling, you cannot go to very low temperature. The temperature has to be of at least of the order of the saddle. So okay, so as I said, you can view this as an open quantum system. So as kind of a distraction, but I think from posters I see some interest in this kind of topic. So you can actually do some non-equilibrium quantum dynamics with this system, a quantum quench, where you can see some localization transition. So what you do is that you take this Hamiltonian and you do a quench where your initial state is in the ground state of the operator that is coupled to the path. So then you let it relax. You connect it to the path and you let the system relax. Then you can see a dynamical phase transition. If the coupling to the path is strong enough, this initial condition will not be forgotten. So the observable couple to the path will not decay to zero. Otherwise, it will decay to zero, and they are separated by a critical point. And so this is really a toy model of the localization or quantum Zeno like a transition, much studied in the spin boson model since the 80s. Now, spin boson model is a kind of difficult model, but in this SYK boson model, thanks to the larger limit, in fact, we can understand almost everything regarding the critical properties of the dynamical transition. For example, we can predict where the critical point is, and we know how the order parameter scale, the order parameter exponents. From 2 slides ago, I told you about this correlation time exponent divergence. with this you can figure out what is the how this order parameter decays at criticality as algebraically as a function of time. So you can essentially, this is like an Ising transition. You have two independent exponents. So if you know these two, you can use scaling relation to figure out that one. Okay. So this instability exists in SYK-like models, and we can understand it, and we can even use it to do some non-equilibrium dynamics. So let's come back to the question. But can we use this? Yes, I'm finished. This is the last slide. Can we use this to reach fast scrambling? So as I told you from that from the okay. Good to be able to go back to this slide. As I told you from this slide, if you just have this picture, it's not obvious because you cannot really go to very low temperature. If you fix J over minus JC, then if the temperature is much lower than this, then the saddle point will not help you, and you are trapped in this minimum where nothing interesting really happens. You cannot have much scrambling. However, what you can do is the following: instead of having one path connecting to your dot, you can connect it to many paths, and now these paths are monitoring coupled to observables which are not commuting with each other. Okay, so you take independent copies of this random fermion binomials and you couple to different paths, and you should take a lot of them. You should take as many boson degrees of freedom as fermion degrees of freedom. At least they should be proportional. So then what will happen before the effective potential for the boson is very easy to draw. It's one-dimensional, and you can have a symmetry breaking. Now it is m-dimensional. So the boson, so at the low temperature, the boson would like to go to one of the direction, but the boson is really frustrated because every dimension is equally favorable. So as a result, I didn't show you the calculation, but it was, in fact, it was found independently in a series of papers in 0+ dimension, and we also we extended that into 1+ dimension, 1+1 dimension using large N techniques. So you can do the calculation, and you do the calculation, you find that the bosons are no longer classical, but they become quantum and they become critical. And then you can calculate scrambling in using large N techniques, so summing diagrams. You can find the maximal chaotic. You can find the fast scrambling on maximal chaos. And these states are really comparable to low temperature states of SYK. So in fact, you can also show that if m goes to infinity, you really retrieve the SYK. So if there's one thing that you should take home on SYK from this talk is that a good way to view it is to view it as some fermionic degrees of freedom coupled to bosonic degrees of freedom, and then the interaction comes from there. So what I cannot answer is that can we build some classical description of this kind of fast scrambling, because the main point is that now the boson become quantum, and this kind of nice picture you can draw about one classical degrees of freedom coupled to some fermions. A priori they do not work. So this is the speculation I'm talking about. I suspect that if you take m to be much smaller than n, but still greater than 1, you might be able to get some classical description, but I don't know the details. Okay, so that's all. Take home message: scrambling is not chaos. instabilities also exist in SYK-like models. They are not hard to understand, but if you want to reach fast scrambling, you need to work harder. You can try to understand it as a limit of such instabilities, maybe which we should call marginal. So okay, thank you for your attention.
Silvia?
Okay, so in the first part, you define a quantum and a classical square commutator that have a different definition, and what the quantum one is the length of the string. So I was wondering, what's the meaning in fully connected model of that? And the second question, what happens if you didn't understand anything? So the first is, what's the meaning of the quantum square commutator that you define for all-to-all models? So what's the quantum? So since there you don't have this picture of the string.
Yeah, for the quantum one, it's better to understand it as operator size, right?
But okay, but there it's full all-to-all, so you don't have this picture of the size.
You can always have a picture of operator size regardless of interaction, right? I don't understand.
Okay, maybe I will tell you. But and what happens if you compute the classical one for on the sphere inside the sphere?
Oh, inside the sphere, you get a smaller exponent, and at some point it disappears because it becomes too slow.
No questions? I have my own question. So when you showed the dynamic transition when in the interpretation of the coupling to the bath, that one. No,
okay.
Yes, this one here. So I sort of remember that when you looked at, say, a spin chain coupled to a bath, so each of the spins coupled to a bosonic bath, there was a critical line that depends on the coupling to the bath, and that the exponents on this coupling, on this critical line, were changing. You don't see something like that.
No,
you always see the same.
I think
It's because of fully connected.
Yeah, this is much more mean field than it's really the basic Lerner-Ginsburg type criticality.
Yeah,
it's the simplest toy model that you can write on. Yes.
Nice. Other questions? Yeah.
No, I was just confused. I didn't understand this classical OTOC is not the square of the Poisson bracket.
Yeah, it's almost the same. So it's something that is really under the rug. That so you see the classical one, you compute it with the big spin S operator, and then you take the square. And this everything here exists as operators on that small Hilbert space of spin S. And you can easily make classical phase representation of that. But this is the OTOC which people calculate in, for example, SYK, and it's not the same. You at some intermediate step, you go out of that space of a symmetric operators or states. So you. Yeah, you have to work a bit differently on that, even in this classical model.